Hello. Welcome to the 6th lecture of my Mathematics of Lattice-Based Cryptography course. In this lecture, I'll present Ring-SIS and Ring-LWE, the variants of SIS and LWE, where integers modulo a prime q are replaced by polynomials in a certain polynomial ring. I'll also explain why Ring-SIS and Ring-LWE can be considered to be problems in certain structured lattices called anti-cyclic lattices. Recall the LWE-based public key encryption scheme due to Lindner and Peikert. One significant drawback of the scheme is that the encryption takes place one bit at a time. One can't do much better because the plaintext is hidden in the ciphertext component C2. Since B transpose times R plus Z primed is an integer modulo Q, and decryption needs to handle the errors introduced in the encryption process, one can't do much better than adding a single plaintext bit, suitably scaled. The idea behind the module version of LWE is to replace ZQ elements in LWE with polynomials of degree less than n, whose coefficients are in ZQ. The quantity B transpose R plus Z primed in the ciphertext component C2 is now a polynomial of degree at most 255, and so it has 256 coefficients. Thus, a plaintext bit, suitably scaled, can be added to each coefficient. In this way, encryption can be done 256 bits at a time. This is sufficient for most applications because public key encryption is generally only used to encrypt keys for symmetric key algorithms, and these keys are at most 256 bits in length. I'll next introduce the ring versions of SIS and LWE, and then in Lecture 7, I'll introduce their module versions. I'll begin by defining polynomial rings and ideals. We'll then see how ideals can be viewed as lattices. Zx denotes the set of polynomials with indeterminate x and integer coefficients. Zx is an infinite ring. Let f be a monic polynomial of degree n in Zx. Monic means that the leading coefficient of f is 1. The polynomial ring Zx modulo f, which I'll call R, is comprised of the set of all polynomials in Zx of degree less than n, and where multiplication of polynomials is performed modulo f. So, to multiply polynomials a and b in the ring R, we'll first multiply using ordinary polynomial multiplication to get a polynomial h of degree at most 2n minus 2, and then divide h by f to get a remainder polynomial r of degree at most n minus 1. Then, the product of a and b is defined to be the remainder r. On a computer, one represents polynomials by their vector of coefficients. So polynomials in the ring R can be represented by a vector of length exactly n, where the components of the vector are integers. I'll often switch between polynomials and vectors using this association. For example, consider the ring of polynomials modulo x to the fourth plus 2x squared minus 11x plus 1. So the ring R is comprised of polynomials of degree at most 3 with integer coefficients, and where multiplication is performed modulo the degree 4 reduction polynomial. The polynomials a and b can be represented by length 4 vectors of integers. Addition and subtraction of a and b is component-wise. You can check that this is the product of a and b. An ideal I in the polynomial ring R is a subset of R that contains the zero polynomial, is closed under addition and subtraction, and is closed under multiplication by elements in the ring R. So for all elements A in the ideal and elements R in the ring, the product A times R is also in the ideal. For example, let A be a ring element. Then you can verify that the set of all multiples of A is an ideal of R. This ideal is called the principal ideal generated by A. Similarly, let A1 and A2 be ring elements. Then you can verify that the set of all linear combinations of A1 and A2, where the coefficients of the linear combinations are ring elements, is an ideal of R. This ideal is called the ideal generated by A1 and A2. Ideals can be viewed as lattices. More precisely, if I is a non-zero ideal of the polynomial ring R, then the set of vectors corresponding to the polynomials in the ideal form a lattice, called an ideal lattice. This set of vectors is a lattice because it's closed under addition and subtraction, and therefore is an additive subgroup, and also discrete, since it's comprised of integer vectors. However, an ideal lattice isn't necessarily full rank. In the next few slides, we'll only be concerned with cyclic lattices, where the reduction polynomial is x to the n minus 1. Then, in the remainder of this course, we will study anti-cyclic lattices, where the reduction polynomial is x to the n plus 1. We'll first investigate cyclic lattices. A lattice is cyclic if it is closed under the operation of right cyclic shifts. Cyclic lattices, which are examples of structured lattices, were first studied by Michiancho in 2002. It turns out that every ideal lattice is cyclic. Let's prove the statement. Let V be a vector in an ideal lattice corresponding to an ideal I. Recall that the components of V are the coefficients of a polynomial V of x that is in the ideal I. Now, multiplying V of x by x yields the polynomial V0x plus V1x squared plus Vn minus 1 x to the n. Since we are working in the ring R, we can replace x to the n by 1, yielding this polynomial, whose vector representation is the right cyclic shift of V. Since I is an ideal, it is closed under multiplication by polynomials in R. In particular, it is closed under multiplication by the polynomial x. Thus, x times V is in the ideal, so its vector representation is in the lattice. This proves that L is closed under the operation of right cyclic shifts. Let's proceed to find the basis matrix for a lattice L of a principal ideal I generated by A of x. The ideal is the set of all polynomial multiples of A. Now, if R of x is a polynomial in the ring R, then A of x times R of x can be written like this. Thus, A of x times R of x is a linear combination of the polynomials A, x times A, x squared times A, up to x to the n minus 1 times A. It follows that the vector representations of these polynomials are a spanning set for the lattice. Let A be the n by n matrix whose columns are the vector representations of the polynomials A, xa, up to x to the n minus 1 times A. A is called a circulant matrix, denoted circ A. Note that a row of A is a right cyclic shift of the previous row. It turns out that A is invertible if and only if A of x and x to the n minus 1 are relatively prime over the rational numbers. So the lattice with basis matrix A is a full rank lattice if and only if A of x and x to the n minus 1 are relatively prime. We'll henceforth assume that A of x and x to the n minus 1 are indeed relatively prime. Now, if R is a length n integer vector, then A times R is this integer linear combination of the columns of A. The corresponding polynomial representations are R0 times A, R1 times x times a, up to Rn minus 1 times x to the n minus 1 times a, which is equal to a times r modulo x to the n minus 1. So the lattice L of the principal ideal generated by A of x is a full-rank cyclic lattice with basis matrix A that is circulant. More generally, suppose that A1 up to AL are polynomials that are relatively prime with x to the n minus 1, and let I be the ideal generated by them. Let M equals L times n, and let A be the n by m matrix obtained by concatenating the circulant matrices corresponding to A1, A2 up to AL. Then, for integer vectors R1, R2 up to RL, the vector A1 times R1 plus A2 times R2 plus AL times RL corresponds to the polynomial A1 R1 plus AL RL modulo x to the n minus 1. Thus, the lattice L of the ideal generated by the polynomials A1 up to AL is a full-rank cyclic lattice with basis matrix A. Now, let Q be a prime number such that 2 to the m is greater than Q to the n. Consider the function HA that maps a binary string z of length m to the length n vector a times z modulo q. HA is a compression function since the domain is larger than the codomain. Michiancho proved that HA is a one-way function on average, assuming that a certain lattice problem in cyclic lattices is hard in the worst case. However, it turns out that HA is not collision resistant. Collisions can be found because the sum of the entries in a row of a circulant matrix is constant. In other words, the circulant matrix AI times the all ones vector is a vector all of whose entries are equal to Ci. To find a collision for HA, one only needs to find integers xi between -1 and 1, for which x1 times c1 plus x2 times c2 plus xl times cl is equal to 0 modulo q. At least one of the xi should be 1, and at least one should be -1. This should be easy to do. Then, let z be the length m vector, where zi is the length n vector, all of whose components are xi. Note that a times z is 0 modulo q. Then you can check that R1, R2 defined here is a collision for HA. An anti-cyclic lattice is a lattice that is closed under the operation that cyclically rotates the coordinates and negates the cycled element. These lattices were first studied by Lobachevsky and Michiancho in 2006. Anti-cyclic lattices are structured lattices. I claim that every ideal lattice in the polynomial ring Zx modulo x to the n plus 1 is anti-cyclic. Let's prove this claim. Let V be a vector in an ideal lattice corresponding to an ideal I. Recall that the components of V are the coefficients of a polynomial V of x in the ideal I. Now, multiplying V of x by x yields the polynomial V0x plus V1x squared plus Vn minus 1 x to the n. Since we are working in the ring R, we can replace x to the n by -1, yielding this polynomial whose vector representation is a right cyclic shift of V, with the cycled element Vn minus 1 negated. Since I is an ideal, it is closed under multiplication by polynomials in R. In particular, it is closed under multiplication by the polynomial x. Thus, x times v is in the ideal, so its vector representation is in the lattice. This proves that L is closed under the operation that cyclically rotates the coordinates of a lattice element and negates the cycled element. Suppose now that n is a power of 2. Then x to the n plus 1 is irreducible over the rational numbers. I'll remark that x to the n plus 1 is the 2nth cyclotomic polynomial. Let a of x be a polynomial, and let I be the principal ideal generated by a. As was the case with cyclic lattices, the vector representations of a, x times a, up to x to the n minus a is a spanning set for L. A consequence of a of x and x to the n plus 1 being relatively prime is that the vectors are linearly independent. Thus, these vectors are a basis for the lattice L. Now, let A be the n times n matrix whose columns are the vector representations of the basis vectors. A is a basis matrix for the ideal lattice L of I. Such a matrix A is called an anti-circulant matrix. Notice that unlike the case with circulant matrices, the row sums and the column sums of an anti-circulant matrix are not equal. For example, let's consider the ring of polynomials modulo x to the fourth plus 1. Let A be this ring element. Then the anti-circulant matrix corresponding to the polynomial A is this 4 by 4 matrix. Let R be this ring element. You can check that the product of A and R in the ring is this polynomial. And you can check that you get its vector representation by multiplying the matrix A and the vector representation of the polynomial R. More generally, let A1, A2 up to AL be non-zero polynomials in R. Let I be the ideal generated by A1 up to AL. Let M equals L times N, and let A be the N by M matrix obtained by concatenating the anti-circulant matrices corresponding to the polynomials A1 up to AL. Then the ideal lattice corresponding to the ideal I is a full-rank anti-cyclic integer lattice with basis matrix A. These structured lattices are used to define the Ring-SIS problem. To define the ring versions of SIS and LWE, I'll need the notion of size for polynomials. The symmetric mod representation of an integer r modulo q is defined to be r itself if r is at most q minus 1 over 2, and q minus r if r is greater than q minus 1 over 2. So r mod sq is between minus q minus 1 over 2 and q minus 1 over 2. The size of an integer r modulo q is defined to be the absolute value of the symmetric mod representation of R. This is also called the infinity norm of R. For example, if Q is 23, then the size of 3 is 3, whereas the size of 19 is 4, since the symmetric mod 23 representation of 19 is minus 4, and its absolute value is 4. The size of a polynomial A is the maximum of the sizes of its coefficients. For example, the size of this polynomial is 4. The ring version of SIS was introduced by Lubavchevsky and Michiancho and by Pikert and Rosen in 2006. The Ring-SIS problem is the following. Given L randomly selected polynomials A1 up to AL, find small polynomials Z1 up to ZL, such that A1Z1 plus A2Z2 plus ALZL equals 0 modulo Q. Here, small means that all the coefficients of the Zi polynomials are between minus b and b. Also, to rule out the trivial solution, the Zi should not all be 0. Note that if we have one Ring-SIS solution, then we can get some more solutions by multiplying the components of a solution by x or minus x. In this way, one solution produces up to 2n minus 1 other solutions. The matrix form of Ring-SIS is the following. Let A be the n by m matrix, where m equals L times n, obtained by concatenating the anti-circulant matrices corresponding to the polynomials A1 to AL. Then, the Ring-SIS problem is to find a small vector z in the null space of A modulo Q. So Ring-SIS is a special case of SIS, where the matrix A is structured, namely comprised of anti-circulant matrices. Lobachevsky and Michancho proved that solving Ring-SIS on average is at least as hard as solving a prox SVP for anti-cyclic lattices in the worst case. As with the worst case to average case reduction for SIS, this guarantee is an asymptotic one. Here's an example of Ring-SIS. Let's take Q to be 59, N to be 4. So the ring of polynomials RQ is the polynomials over Z59, modulo x to the 4th plus 1. We'll take L equals 3, so M equals L times N, which is 12. And we'll take B to be 2. The three randomly selected polynomials are A1, A2, and A3. So the Ring-SIS problem asks us to find small polynomials Z1, Z2, and Z3, such that A1, Z1 plus A2, Z2 plus A3, Z3 is 0 modulo 59. Here, small means that the coefficients are between -2 and 2. The matrix A is this 4 by 12 matrix. We need to find small vectors in the null space of A modulo Q. I used Gaussian elimination on A modulo 59 to get this reduced form matrix A primed. As expected, A primed has rank 4, and so its null space has dimension 8. The independent variables are R5, R6, up to R12, and the dependent variables are R1, R2, R3, and R4. The total number of solutions is Q to the 8, which is about 146 trillion. Of these, there are 24 non-zero solutions R, all of whose components are between -2 and 2. Up to multiplication by plus or minus 1, plus or minus x squared, and plus or minus x cubed, the three SIS solutions are R1, R2, and R3. The polynomial form solution corresponding to the first solution R1 is Z1, Z2, and Z3. You can check that A times R1 is 0 modulo Q, and also that A1Z1 plus A2Z2 plus A3Z3 is 0 in the ring RQ. I'll next define a hash function which can be proven to be collision resistant under the assumption that Ring-SIS is hard. Let Q be a prime and let L be greater than log Q. A1, A2 up to AL are randomly selected polynomials, and let M be L times N. A is the n by m matrix formed by concatenating the anti-circulant matrices corresponding to the polynomials A1, A2 up to AL. The hash function HA maps a binary string Z of length m to the vector A times Z modulo Q. As an exercise, you can prove that HA is collision resistant under the assumption that Ring-SIS is hard on average. Combined with the worst case to average case reduction of Lobachevsky and Michancho, establishes that HA is collision resistant on average, provided that a prox SVP for anti-cyclic lattices is hard in the worst case. In summary, two advantages of Ring-SIS over SIS for cryptographic applications are the following. In SIS, the matrix A has a storage cost of m times n ZQ elements, whereas in Ring-SIS, the matrix A has a storage cost of L times n, which is m ZQ elements. This is because an anti-circulant matrix can be derived from its first row. In SIS, multiplying A by a vector R modulo Q has running time m times n ZQ operations. Whereas in Ring-SIS, A times R modulo Q can be computed in time m times log n using the number theoretic transform. A drawback of Ring-SIS is that the matrix A is structured. However, no algorithms, either classical or quantum, are known for solving Ring-SIS that are any faster than the best algorithms known for solving SIS. The ring variant of LWE was proposed by Lubashevsky, Pikert, and Rosen in 2010. Let SB denote the polynomials whose coefficients in mod S representation are between -b and b. I'll call these the small polynomials. Ring-LWE is the following problem. Let S be a randomly selected polynomial, and let E1, E2 up to Ek be k randomly selected small polynomials, so their coefficients are between -b and b. Let A1 up to Ak be randomly selected polynomials, and define Bi to be Ai times S plus Ei. Given the Ai and the Bi, the problem is to determine the polynomial S. The matrix form of Ring-LWE is the following. Solve the equation As plus E equals B modulo Q, where A is the matrix obtained from the anti-circulant matrices corresponding to the polynomials Ai, and the vector B is obtained from the coefficients of the Bi. Note that A is a Kn by n matrix. You can see that Ring-LWE is a special case of LWE, where the matrix A is structured, namely comprised of anti-circulant matrices. Here's an example of Ring-LWE. Let's take Q to be the prime 17 and n to be 4. So the ring of polynomials RQ is the polynomials over Z17 modulo x to the fourth plus 1. We'll take K to be 3 and error-bound B to be 3. The Ring-LWE instance is comprised of the three pairs of polynomials A1B1, A2B2, and A3B3. The Ring-LWE problem asks us to find a polynomial S such that Bi minus Ai times S is a small error polynomial. In other words, Ei has coefficients between -3 and 3. Here are the matrices A and B for this Ring-LWE instance. We need to solve the equation As plus E equals B modulo Q for S and E, where the components of E must be between -3 and 3. It turns out that there are two Ring-LWE solutions shown here. The polynomial form of the first solution is S, E1, E2, and E3. You can check that As plus E equals B modulo Q, and that Ai times S plus Ei equals Bi for I equals 1, 2, and 3. Lubashevsky, Pikert, and Rosen proved that solving Ring-LWE on average is at least as hard as quantumly solving a prox SIVP for anti-cyclic lattices in the worst case. As with the worst case to average case reduction for LWE, this guarantee is an asymptotic one. Even though the matrix A in Ring-LWE is structured, no algorithm, either classical or quantum, is known for solving Ring-LWE that is any faster than the best algorithms known for solving LWE. Ring-LWE has the same advantages over LWE as Ring-SIS has over SIS. Namely, the matrix A requires less storage, and multiplying the matrix A by a vector R modulo Q can be sped up by using the number theoretic transform. To conclude this lecture, let me outline the linear Picot public key encryption scheme using Ring-LWE as the underlying problem. This scheme can encrypt n-bit messages in contrast to the LWE-based scheme, which only encrypts 1-bit messages. In key generation, an entity Alice selects random small polynomials S and E, and a random polynomial A, and computes the polynomial B equals AS plus E. Her public key is AB, whereas her private key is S. Suppose now that Bob wishes to encrypt a length n binary string M for Alice. The plaintext M can be viewed as a polynomial of degree less than n with 0,1 coefficients. Bob first obtains an authentic copy of Alice's public key, AB. He selects random small polynomials R, Z, and Z primed. He then computes C1 equals AR plus Z, and C2 equals B times R plus Z primed plus M times Q over 2. Note that each coefficient of the plaintext polynomial M has been scaled by multiplying it by Q over 2. The ciphertext is comprised of C1 and C2. To decrypt C, Alice uses her private key S to compute C2 minus S times C1, and then rounds the coefficients of the resulting polynomial. As an exercise, you can prove that the encryption scheme is indistinguishable against chosen plaintext attacks, assuming that the decisional short secret Ring-LWE problem is hard.